Good morning, physics students. I am recapping the lab that we did where we shot the rubber band into the plastic cup. The very first question in your lab, once you were trying to do the lab, was to develop a pie chart for the situation. So if we started one level above that, which would be the schema and trying to define the system, we would define the system by saying rubber band, cup, table. Once you do that, we could then do the pie chart for the situation. When you stretch the rubber band on your finger, you gave that rubber band 100% elastic energy. And then we shot the rubber band into the cup, which made the cup move. So the elastic energy transferred 100% into kinetic energy. If we were to develop a formula for each of these types of energies, the elastic energy, we know the formula 1/2 kx squared is equal to energy. And since the elastic energy became kinetic energy, I know that 1/2 kx squared is going to be equal to the formula for kinetic energy, which is 1/2 mv squared. That brings us to the first question that you were supposed to answer with math, which is to calculate the spring constant k for distance 1. When they're referring to distance 1 on the data table, they're referring to how far back you pulled the rubber band. That's the thing that was distance 1. So if I'm trying to solve for k, I'm going to have to do some algebra to isolate k on one side of the equation. I'm going to divide by 1/2 x squared, and when I do that, the 1/2s would cancel out and the x squareds would cancel out. And of course, if I do it on that side of the equation, I need to do that same thing on the other side of the equation. So what I end up with is a formula that looks like this: k equals 1/2 mv squared over 1/2 x squared. The 1/2s would also cancel out, so the formula simplifies even further to just mv squared over x squared. The mass, of course, would have to be in kilograms, since when we're working with newtons and joules, the subunit in there is kilograms. Units are important. I saw a lot of people doing math without this number in kilograms. And also make sure that your velocities are in meters per second. Not centimeters per second, but meters per second. Again, newtons and joules are kilogram meters per second squared or kilogram meters squared per second squared. So your units are important. Lastly, when dealing with the distances over here, these are also going to have to be in meters. So, plugging in my numbers: mass of 0.003, velocity of 1.94, distance I pulled back the rubber band, 0.15. I'll let you do that math, but you get a spring constant. I did the exact same thing for the second spring, or the second distance, where I pulled it back 0.2. And when I pulled it back 0.2, the cup went with a velocity of 2.58. That makes sense. The more energy I gave to the rubber band, the more energy the cup had, so it was moving faster. I'll let you do that math to figure out what the spring constant was. Make sure when you're doing this math on your own lab that you do have the right units. I'm going to go over those one more time. The mass needs to be in kilograms. Your velocity needs to be in meters per second. And finally, the stretch of the rubber band also needs to be in meters. We're supposed to do this one more time, where I put in 3.23 for my velocity, because when you pulled the rubber band back 0.25 meters, the cup moved even faster. Make sure you have your lab complete before the next class period. I will be collecting them and putting some points into the gradebook for your completed work. Thanks. Bye.